punto, capito? Vabbè. Questa. No.
Ma sì, accendo sotto. Vuoi darmi questo? Vuoi tenere tu quello? Sicuro?
Guarda. Allora. Master Environment.
Esatto, un PDF semplice, così cominci proprio con le cose facili. Invece del keynote.
Sì, però come si apre? Perché vedi, tu dici...
Fai comando O.
No.
Metti clicca qui sopra, selezionalo, fermo.
No, scusa, conto, aspetta.
No, aspetta.
No,
Comando O. Non lo hai aperto.
No, ma si fa così.
Anche O.
Dov'è? So, beta è rimasta su.
Aspetta, faccio così. No.
Non funziona?
No.
We have to begin the second part of the morning. So let's start. The first talk is by Francesco Massaro, Dragon's Lair on the large-scale environment of BLAC.
Okay. Does it work? Yeah. Okay, great. Thanks. So thanks a lot. Thanks to the organizer for the very nice conference. I just arrived. And I wish to start thanking all the collaborators. I mean, without their help, I wouldn't never done this. This is the story of a discovery that took me about 10 years to carry out. So, and actually, this is my first talk at the NAG9 conference. And see, okay, this is also the first time I'm giving a sort of inverted talk. Okay, I will tell the question we want to answer, I will tell the answer, and then I will try to convince you about the analysis we carried out. Probably I suffered too much the influence of one of my collaborators that was pushing me to make things very neat. Okay, sorry, the outline of the talk is this one, and of course, I mean, I will just briefly overview the BLAC in the AGN unification scenario, talking about environment and intrinsic properties. Then I will give you the results, what we learn from the large-scale environment of BLACs, a sort of test for the AGN unification scenario, and then step by step, some of the biases, the artifacts we have been found during the analysis. I couldn't start the talk without the classical plot of the AGN unification scenario, and I mean, I just want to focus on blazars and radio galaxies, so only on radio loud AGNs, and in particular, I want to focus on BLACs and radio galaxies FR1 type, the edge darkened ones. So if you look through the jet, you're going to see the BLAC. If you look on one side, so if the jet is not pointing toward you, you're going to see a radio galaxy. And at the very, very zero order, the classification scenario, the unification scenario and the classification of the objects is just driven by the inclination along the line of sight. So in principle, you have radio galaxies like the one on the left, and FR1, if it's pointing toward you, in the optical you would see something like this, so all the emission lines will be blended by the continuum of the jet. Okay, we have been listening about these objects in several talks before. So if this is true, the environment at large scale should be exactly the same. So, and this is the test I want to carry out on these two kind of galaxies, you know, FR1s and BLACs. The answer is no. Basically, the environment on large scale is completely different. So BLACs are not radio galaxies pointing toward us. This is an example. This is the case of two optical images. In the two optical images, there are two circles, 500 kiloparsec and 1 megaparsec at the redshift of the source. The one on the left is a BLAC. The one on the right is an FR1 radio galaxy. And you see in red, those are sources with a redshift, almost the same redshift of the central radio galaxy, okay, within 5 10 to the minus 3. That corresponds roughly to 1,500 kilometers per second as velocity dispersion. This is one example, okay? All the other sources I'm going to do, I just did a test using different catalogs to show that this is systematic. So every time you plot a radio galaxy and a BLAC, if you compare them in the same redshift bin, their environment is different. Radio galaxies live actually in environments that are richer. And this is the result. So in this plot, you're going to see a measurement of the richness. This is the number of cosmological neighbors, that means galaxies with the same redshift of the central galaxy. This is the median value within 500 kiloparsec. And we did this in 500 kiloparsec, 1 megaparsec, and 2 megaparsec. This is the median value as function of redshift. The blue dots here are the BLACs, and they are systematically below the radio galaxies that are these other dots. The FR1 radio galaxies. We also did the test for the LERGs, so for the low excitation radio galaxies. And I want to highlight, this plot must be seen from this direction. So it must be seen redshift point per redshift bin per redshift bin. You cannot compare these systematically. You cannot compare the entire sample because the richness when you estimate a certain redshift is completely different from the one that you can estimate by redshift. So the solution of the problem, if the BLACs are not the counterpart of the FR1 radio galaxies, then what are their counterparts? And the solution is they are very, very similar to the FR0s. So radio galaxies lacking extended emission of the order of 10 kiloparsec, just bright spots in the radio. And, sorry, pointing out, this is the same plot before, and this is the BLACs and almost the same line. For the statistical analysis, we carried out a Mann-Whitney test in order to compare the medians. It's a non-parametric test, rank test. So, okay, now how to carry out the analysis. A friend of mine a long time ago suggested to do this. You take a radio galaxy catalog, you take a galaxy cluster catalog, you shake them, you make the comparison between radio galaxies, how many radio galaxies lie in galaxy cluster. Then you repeat the same for BLACs, and then you can find an answer. This is not possible. First of all, the main problem we found is there is no radio galaxy catalog on FR1s. So long time ago, we had to build the radio galaxy catalog. Then we need to find a galaxy cluster catalogs, and there are several in the literature. And this was another problem, because the galaxy cluster catalogs, they can have uncertainties, and they can have biases, they can have artifacts in the algorithm used to draw the galaxy clusters. This is one of the worst examples, actually taken from what I believe is the best catalog of galaxy cluster I found in the Sloan footprint. So the red dots that you see with the redshifted NGAL are just the galaxy clusters found by the automatic algorithm, and the NGAL is the richness given in the galaxy cluster catalog. While the red dots that you see, the red dots are just the sources, the cosmological neighbors, so the sources with the same redshift of the central objects within 5 10 to the minus 3 in redshift difference. So you see completely different position, and the cluster is basically broken, okay? So you need to recover this before using the catalog, and you need to check source by source. That's what we did. Let me skip this. So we have been building this kind of plots, so central radio galaxy or central BLAC, all the sources with a redshift, and we have been checking all these plots for all the radio galaxies and all the BLACs in the sample we compared. In addition, even if I'm not going to show this, we also test the red sequence, we also test different clustering algorithms like DBScan, MST, all the same results. This is something that you cannot do, and people did in the literature, old-fashioned. You can count the magnitude, you can measure the magnitude of the central galaxy and say something like +2, and then count all the galaxies around within a range of magnitude, and then you can average an excess or an overdensity of galaxies around the central object. Okay? This cannot be done, especially if you want to take the entire population and claim a systematic excess, as they've been doing. In the y-axis, there is the projected distance. This is the excess of galaxies around the BLX or radio galaxies. This cannot be done. The reason is this. If you compare objects, the central objects, they have a different magnitude, a different redshift range. This means that the signal-to-noise ratio is different. So you are comparing objects at different signal-to-noise. So this is statistically incorrect. Something else that cannot be done, like something like a Bell classes for the richness. If you take the central object and you change the magnitude of the central object, the number of the galaxies around will follow that magnitude, and the magnitude is changing. So you cannot compare objects in this way. You can only do this per redshift bin. And this is my last slide. This is something else. If you take a cluster at redshift 0.034, all the red dots are the cosmological neighbor, sources with the same redshift of the central objects. And then you move a redshift 0.15, and you take into account of the cosmology, fixing the luminosity. This is what is happening. Just one source within a central region of 500 kiloparsec. This is why you need to take into account of redshift. And in fact, for example, this is an estimate of sigma 5, one of the usual parameters to account for dark matter halos. This is redshift dependent. So you cannot compare sources unless you do this in the same redshift bin. If you compare the entire population, it makes no sense. This is why you cannot compare FR1 and FR2 radio galaxies, because they have different luminosity. If you take a survey of the sky, then you will find that all the FR2s will be a higher redshift, a higher luminosity, and so you will always see a dichotomy in the plot. These are FR2s, these are FR1s. So the only way to do is really counting sources with a spectroscopic redshift. That's it.
Thanks, Francesco. Perfect in time. So questions for Francesco?
Hi. So the question is, why didn't you just compute the cross-correlation function between galaxies and your radio sources and do the halo model? So you get the occupation number as a function of the halo mass, and so you would probably get a more complete view.
You mean the two-point correlation function for clustering around?
Yes.
Yeah, no, we did it. We did it as the MST, as a DB scan, and we got the same result. The point is that it's not as strong as using redshift, spectroscopic redshift.
Well, in principle, okay. You do, right, with the correlation function, with the 3D correlation function, and you also reconstruct the number of objects within the halo. It's much more powerful, probably.
Yeah, using coordinates and spectroscopic redshift. No, we have been trying to do this, just did not close the analysis on that. Yeah.
Other questions for Francesco? Okay, just have a curiosity if I miss it. So what is the implication on the physics of the sources if there is a difference? What is the implication on the physics of the sources?
Okay, the environment is not playing the major role, on the sources, okay? So, first of all, BLX are different from FR1s, so you don't expect diffuse emission in the radio. Okay, that's the major point. And different physics. You're looking at different objects than the one you were expecting before.
Okay, thanks again. Let's thank Francesco again. And now, okay, now we have Izzy Garland. What is your... Okay, I'm searching for your... Okay. so I found it. Okay. Sure. Okay. I think the title has changed from what is written in the program. So we have Izzy Garland with secular black hole growth, AGN feedback, and galactic evolution. Please.
Thank you cool. So thank you very much for having me. As you've probably gathered from the programs, I am not Brooke Simmons. She unfortunately couldn't make it. Fortunately, last-minute changes happened, so you're stuck with me instead. I'm one of her PhD students at Lancaster University in the UK, and I will be using my time today to tell you about results from our group and collaborators on supermassive black hole growth and galaxy coevolution, specifically through the lens of secular processes. That is, processes that don't involve mergers. They occur in the absence of mergers. Is there a thing for me to flip? Cool.
Thanks.
Excellent.
Sorry.
Cool. So, for a long time, discussion of merger growth dominated the field, and this was for several reasons, including selection effects, and the fact that mergers can drive all these processes. Like, it's very clear that mergers can and do grow supermassive black holes and galaxies, and this is for several reasons. Oh, cool, the GIF sorted itself out. This is for several reasons, including the rearranging of angular momentum, messing everything up, causing stars to grow, causing black holes to form. But it turns out that mergers might not be the dominant mechanism. But here we've got a couple of samples. There have been so many studies dedicated to merger-driven growth. I can't possibly do them all justice with the time that I have. So here's just a couple of examples that use HST data and find that red radio loud, quasars, a subset of AGN, lie overwhelmingly in merger-dominated environments. So it's, like I say, it's clear that mergers can and do grow these galaxies and these black holes, but it turns out they might not be the dominant process. Actually, we're pretty sure at this point they're not the dominant pathway. So I'm showing a study here from a recent simulation by Martin et al. From the Horizon AGN team. And it's showing that the cumulative black hole growth since redshift about 3 up to the present day, only about 35% of this is due to merger-driven growth. And studies such as McAlpine et al. More recently show that it could be at an even lower level than this. So it's crucial that we understand black hole growth in the absence of major mergers, because it clearly dominates the population. So the problem is isolating this merger-free pathway. And another thing that simulations have shown over the last few years is that a classical bulge, as we know in a galaxy, is an inevitable consequence of a large merger, a significant merger. And in the absence of such a merger, galaxies tend to evolve into bulgeless disk galaxies, such as here in the fire simulations. So if we see a galaxy, if we just observe a galaxy, and it's very strongly disk-dominated, there's not much, or there's no presence of a bulge there, we can assume that it hasn't experienced a significant merger since redshift 2. It's just grown via gas accretion and through micromergers, what we might call, which aren't really significant enough to disturb the disk shape. So we can isolate this merger-free black hole growth pathway by selecting exclusively disk-dominated bulgeless galaxies. And then to get the black hole growth, we select a subsample of those that have AGN. So the sample I'm showing here is a selection of our sample which is observed with Hubble. These are all disk-dominated AGN. Our whole sample's about 100, but if I put them all on there, you wouldn't be able to see any of them. And these are all luminous AGN. In fact, they're so luminous that they're at quasar-like luminosities at the redshifts they have observed, which is relatively local. We also have SDSS fiber spectra, or Lick long-slit spectra, of each of these galaxies. For a couple, we even have IFU data. And for a small handful, we have archival data at wavelengths from sort of X-ray to infrared. So, like I said, they're all luminous, and they're all unobscured AGN, which means that we can estimate their black hole masses. So the first thing we looked at was, are these galaxies co-evolving? And we took their black hole masses that we estimated from single epoch broad lines, and we plotted this against their total stellar mass. And you can see in the black solid line and the black shaded regions, grey shaded regions, which are the best fit line and the 3 sigma uncertainties, that there is evidence for coevolution. And not only is there evidence for coevolution, there is also, if you look at the red dash line, which is the same plot but for AGN hosted in merger-driven galaxies such as ellipticals and S-naughts, and statistically, these two lines are indistinguishable. And the slight difference in their normalization can be accounted for by the different methods that we use to obtain the black hole masses. So, they co-evolve, and they co-evolve in such a similar way to merger-driven processes. But I should note that this is just one study. And not only is it just one study, it's a study that was selected specifically for very luminous AGN, which means you're going to then involve things like selection bias. And other studies doing this sort of work, selecting for different priorities, find different results. So here's the same plot, but with an extra 2 studies overlaid on top. And you can suddenly see that the overall picture is not that clear. And my colleague Matt Thorne, who is also a PhD student at Lancaster and is here today, is working to reconcile these apparent differences in the results obtained by different studies. And he's shown, through careful comparison of simulations and observations, and particularly folding in selection functions, that actually all of these samples are consistent with being drawn from the same underlying sample of supermassive black holes. Now, Matt's writing up his results at the moment, but you can get a sneak peek by checking out his poster, which is available upstairs. But this is just a really good reminder that selection effects are so important, and we really need to consider them in the work that we do. And it's also a nice confirmation that our sample of merger-free AGN are, in fact, consistent with being drawn from the overall underlying population. So we've got these galaxies. We now know what their black holes are doing and forming rapidly. But if the black holes are forming rapidly, what are the host galaxies doing? And this is what I'm working on. So as part of my PhD, I'm looking at how the star formation rate changes in these AGN galaxies, which has proven a challenge given that the AGN are making every attempt to contaminate our measurements of star formation. But after removing these so-called contaminants, obviously they're not contaminants, but they feel like it some days, we can see that the star formation rate of galaxies hosting AGN takes up the same sort of range as disk galaxies that don't host an AGN, as you can see from this plot I've got up here. However, the average star formation rate for the disk galaxies hosting AGN is slightly higher than for that of the inactive disk galaxies. So this is really, really interesting. They're kind of growing their black holes and their galaxies at the same time. And it kind of sort of helps us sort out one side of the coevolution relationship. Yeah, these black holes and these galaxies are growing together. So I also have a poster here, so you can come and talk to me about that at some of the coffee or lunch breaks if you'd like to. This is just one of the interesting results I've found so far on the work I'm doing with these AGN disk galaxies. Now, another really interesting thing to note about our sample is similarly to a sample of AGN in merger-driven systems, about 60% of our AGN show significant evidence of outflows in their O3 components. And we got Keck time to look at this. We used KCWI in a project led by Becky Smethurst, who is an RAS fellow at Oxford. And what you're seeing here is ionization graphs or ionization plots, specifically O3 over H beta. The red colouring is indicative of regions with high star formation, and the blue colouring is indicative of regions of such high line ratios that it's so likely that they're triggered by an AGN. And the thing to notice is the extent of these, like the spatial extent of these outflows. Sorry, is the top button the little laser button?
Sorry, how much?
Yep, thank you. Yes, cool. So yeah, you can see the significant extent of these outflows here. What you can also notice, or you can't notice from these graphs, but I can tell you, is that the power in these outflows is very typical to the same sort of power you would get in AGN hosted in merger-driven samples. So this indicates that they're typically the same. And this is not what we were expecting at all. There's actually several reasons to think that accretion through merger-driven systems would be very different to that in secular systems. So we know this from a 2019 study, also run by Becky, where we used narrowband images of those same little sources you saw before, and we analysed their outflows. And it turns out that they were different to a carefully selected control sample of AGN in merger-driven systems. And this is illustrated by this toy model here. So on the left-hand side, we have secular feeding, so merger-free processes. And the black hole is consistently fed from the disk galaxy in a very consistent matter, all in the same direction. And over time, this leads to eventual spin-up of the black hole. I have timed this really badly. This leads to eventual spin-up of the black hole, increasing the overall accretion efficiency. And in the merger-driven system, because it's being fed from all directions, this leads to the eventual spin down of the black hole. And we don't have data to observe this yet, but what we do have is cosmological simulations. So Becky is currently working with Ricardo Beckman, a JRF fellow at Cambridge, and they're looking at cosmological simulations and separating the samples by the number of mergers they've had in their system. So in the purple, we've got merger-free systems, and in the grey, we've got systems with several mergers. And as you can see, their spins really are different. The toy model was pointing us in the right direction. Merger-free systems have much greater spin-up. And the dream is to observe this directly, but given current facilities and the fact that we'd need a large sample, that's just not currently possible. But what we can do is look at other parameters in the supermassive black hole region that could be affected by this. So a master's student previously in our group, Josh Butterworth, who's now a PhD student at Leiden, looked into this. He looked through the archive data, and it turns out we had XMM data for a very small handful of our sample, as well as for AGN in a couple of our merger-driven samples. So the photon index, you can see, is higher in the control sample, and they could have slightly different slopes in relation to the ionization parameter. But the sample is too small to say with any sort of significance that they are actually different. So we're applying for XMM time this autumn to try and hurry this to get better and more data. So just to sum up, if there is one thing that you take away from this talk today, it's that merger-free supermassive black hole growth is the primary mechanism through which black holes are grown in our universe. And this mostly happens in a way that's very typical to that in merger-driven systems. However, there are some slight differences that persist right down to the tiny scales of the supermassive black hole. So watch this space. Hopefully, we will have some more data soon, and we can really complete this picture of merger-free growth. The future holds so much, and I'm so excited to see where this takes us. Thank you very much for listening to me.
Thanks. So questions for Itzi?
Hi, thank you. Very nice talk. I was wondering, is it possible that some of your bulgeless AGN are actually misclassified because the AGN is dominating the central emission, outshining the bulge?
Yes, so we used not only Galaxy Zoo to kind of get an initial idea of where the bulgeless sample came from, but they were then looked over by a single classifier because there's only 100 in there. So they've all been individually looked at by sort of one single expert classifier. And any that we were like, we're not really sure if they're bulgeless or the AGN, that's a bulge or the AGN is there, we kicked out so that our sample is very, very pure but might not contain all of the bulgeless AGN that we could have potentially done. We went for purity rather than completion.
Thank you.
Last questions for Rizzi?
Hi. Do you think the importance of merger-driven triggering would increase at higher ratios, say ratio 2, 3, 4?
Sorry, can you repeat the question? I couldn't quite
So
hear
you said the merger-free supermassive black hole growth actually dominates the growth of black holes. You think this holds for all redshift?
So obviously at the moment, because we need to understand the morphology so well, we're using high-resolution stuff, which is generally lower redshift, the beautiful Hubble images we can get. At the moment, we can't really take it back observationally further because we currently don't have data that's clear enough on the morphology to truly understand it. But I think simulations will help us sort of tease out the answer there. But I think we will heavily rely on simulations or JWST, I can say that now it's up. So hopefully I'm thinking about, in a couple of years' time, applying for JWST time to get a deeper look at some of these galaxies.
Okay, thanks a lot again. I think we have to move on. I hope you have more time to discuss. We're going to have more time to discuss these issues at the coffee break. Now we have the talk by Vittoria Zanchettini. Okay, Vittoria Zanchettini will talk about the impact of AGN activity in nearby Seyfert galaxies, high-resolution study of the multiphase ISM with Muse, ALMA, and JVLA.
Okay. Thank you. Okay, I'm Maria Vittoria Zanchettini. I am a PhD student at CISA, and today I will talk to you about the impact of the AGN activity in nearby Seyfert galaxy. Just to start, there are strong observational evidence of a strong link between a supermassive black hole and host galaxy and their host galaxy. Just to show, there is the well-known the M-sigma relation. We have the points where the feedback. We have the feeding phase that involve the AGN phase and the star formation, that the feedback, and it implies the injection of energy and momentum into the interstellar medium, circumgalactic medium, or the gas heating or removal. In this context, there are different ways of feedback. We can have radio jets or AGN-driven winds that can drive multi-phase outflows that involve different gas phases, like the neutral, ionized, and cold molecular one. Then the gas in the interstellar medium can be removed, heated up, or distributed, influencing the star formation process itself. And there is some hint about the fact that the ionized outflow are the faster, but the molecular phase is the one that carries the bulk of the mass. To study the feedback, we can have a different approach. We can look to global effects, so integrated properties, and study the scaling relation, or study local effects, so locally modified properties. To do so, we selected the EBIS AGN. We took the EBIS AGN Geo survey that involved 47 AGN RDX rays selected from the integral EBIS AGN catalog in order not to be biased against nuclear obscuration. This sample has a bolometric luminosity above 10 to the 43 arc per second, are local AGN, and the accurate measure of the black hole masses, star mass, star formation rate. Of this sample, we selected, for my PhD thesis, a subset of 10 Seyfert with available Muse and ALMA data in order to perform a multi-phase approach. First of all, in this presentation, we show you the results on two main Seyfert. The first one is the Markarian 509. And this, in my work, I studied mainly the CO221 data from ALMA. As you can see, the ALMA velocity map, the ALMA data can be modeled with a main disk inclined at 44 degrees. We use the 3D Barolo software by Di Tutore Fraternali. Subtracting this main disk to the ALMA data, we found that the inner region can be modeled with a nuclear warp disk, inclined with respect to the main one. And moreover, we find that perturbation to the disk-like kinematics, here report is with a level, that is consistent with the AGN-driven winds in the molecular phase. From literature, we know that it is been reported that these galaxies show also ionized wind and several UFOs component. Putting all together, we can assess that this multiphase outflow is consistent with a momentum conserving wind or radiation pressure on dust, as you can see here from the plot. And we also found that the molecular disk is coincident here in red contours with the ionized gas disk and with the starburst ring that you can see in the map from HSC. And we want to assess the stability of this disk. To do so, we computed the Tumre Q parameter. This parameter, if it is above a critical value, that for the gas phase is between 1 and 3, the disk is stable. For this galaxy, we found that the disk is stable at the nucleus and in the outflow region. We found values between 3.5 and 5, and the velocity dispersion between 30 and 40 km per second, and then is marginally stable at the starburst ring, with values reported in the slide. Then we analyzed also the local Seyfert galaxy NGC 2992. In this case, it is an object very well studied in X-ray, and from X-ray analysis, it is reported a variable nuclear continuum in the UFOs component. In my work, instead analyzed the different set of data. First of all, the GVLA emission at 6 centimeters that you can see here. This is the map shows the radio 8-shape structure of about 1 kiloparsec nuclear radio jet. Then the point is that the emission in the red circle is well aligned with the ALMA continuum map 1.3 millimeter that traces the cold dust component in the inclined disk. And also there are hints of emission in the cold dust also within the radio jets. Going further, the magenta contours show the ALMA CO221 emission at 100 parsec resolution. They trace the molecular gas disk and outflow. As you can see, the disk is perpendicular to the warm ionized biconical cones that you can see from O3 Muse data. But the radio jet is not. Is inclined also respected to biconical cones. So to put all together, we model also in this case the disk-like kinematics for both the molecular and the ionized component. And we found that the molecular ionized disk have the same inclination and similar velocity rotation, but the ionized gas phase show a higher velocity dispersion. Moreover, we found in the inner region inner circular nuclear ring in the molecular phase, and hints of molecular outflows at the basis of the cones that you can see in the ionized phase that are not modeled by the disk-like kinematics, of course. Okay, what you want to do, of course, is assess the global baryon budget. We did it for the molecular phase, and now we want to do it for also the ionized gas phase. In this case, to do so, we have computed the electron density. In this case, we used the approach from Barron and Netzer 2019, computing the ionization parameter and applying Voronoi tessellation using a signal-to-noise ratio of 10. What we found is that the electron density value vary between the two cones and exceed a value of 10 to the 3 in the inner regions. And this is why we cannot use the SO doublet as a proxy of the electron density. And this work is still ongoing. We have to derive the outflow rate both for the molecular and for the ionized gas phase. Okay, so, and to put this in a wider context, I report here the plot from Hubler et al. 2019, when you can see the velocity dispersion as a function of the redshift for star-forming galaxy. In red, the value for the ionized gas, and in black, the value for the molecular gas phase. As you can see, there are a few measurements for the molecular gas phases, and even less if you take into account AGN's host. So, we want to understand if these values is higher in AGN host galaxies. Using our results, that there are only for 2 galaxies, of course, we found that both the molecular velocity dispersion and the ionized gas dispersion are higher with respect to the one in star-forming galaxy. Both in the disk, here the velocity dispersion is computed at 1 kiloparsec, and both at the nuclear region, when at nearly 200 parsec, is even worse. So this is a hint that one of the effects of the agent-driven winds is to increase the gas turbulence both at the nucleus and over the disk. Of course, this is the results are from only for 2 objects. What you want to do is to assess this value for the whole for all our sample. And so to conclude, this is my conclusion, and I thank you for the attention.
Okay, questions for Vittoria? Fabrizio down there. Wait.
This one? Okay.
I really don't have a particular question, but it looked like a complicated plot to me, and I didn't realize.
Yeah. Okay.
I mean, you said that there is a clear evidence that in AGN.
Okay.
I don't
the
see
red
the
points,
evidence.
the red and black points are for star-forming galaxies from Hubler et al. 2019. The red one are for ionized gas, and the black one for the molecular gas. Then the blue points are for AGN host at higher redshift at 1.5 and 2.3. And then the green points and the magenta points are from my work on Seyfert galaxy in the local universe. So as you can see, the green point and the magenta points are above the relation found for star-forming galaxies.
But how many sources you plan to investigate in this way to have a statistical?
Okay, just to start, the whole subset we found, because the problem, we want a multiphase approach. So we want to have objects with both ALMA at high resolution observation and MUSE. And that's the point. So we will start with these 10 galaxies, and then we will see what we found.
Very last questions for Vittoria? Otherwise, we move on. Thanks again. So the next talk is by Milena Valentini, Host Galaxies of High Redshift Quasars, Supermassive Black Holes Growth and Field.
Okay. Good morning, everybody. I'm Milena Valentini, an Alexander von Humboldt Fellow at the University Observatory of Munich. And today I'll discuss the impact of quasar feedback in the high redshift universe from cosmological simulations. A few hundred quasars have been observed in the last decades at high redshift, and they have been studied by means of multi-wavelength observations. With high redshift, I refer to redshift 6 and above. These observations suggest that these active galactic nuclei have high bolometric luminosities as high as 10 to the 46 per second and are powered by supermassive black holes with mass in the range of 10 to the 8 to 10 to the 10 solar masses. Of course, the presence of these black holes, which grow supermassive in less than 1 gigayear, puts constraints on the theoretical models of the formation of supermassive black holes and challenges the theory of black hole evolution, especially as for the mass of the initial seeds of these supermassive black holes and as for the maximum accretion rates that these black holes have to have in order to reach the final observed masses. The presence of these supermassive black holes in the high redshift universe is tightly connected to the early stages of the black hole galaxy coevolution. And recent observational facilities like ALMA have allowed us to investigate the physical properties of quasar-host galaxies. These observations have shown that these quasar-host galaxies are characterized by dynamical masses of up to 10 to the 11 solar masses. They have a multiphase interstellar medium, dust, and they host galactic scale outflows, which represent one of the main signatures of the ongoing activity of AGN feedback. The observational scenario that I've just outlined motivated our numerical study. We simulated the formation and evolution of a high redshift host quasar and focused our analysis at redshift 6. These are some of the questions that we addressed with our work. So as for the initial conditions of our simulations, they describe a dark matter halo, which is as massive as 10 to the 12 solar masses at redshift 6. We carried out our cosmological hydrodynamical simulations with the gadgetry code, and we adopted a sub-resolution model to account for all those physical processes which occur below the resolution limit of our simulation. Our sub-resolution model describes a multiphase interstellar medium, as you can see from these sketches, and it accounts for several physical processes, such as an H2-base star formation, thermal and kinetic stellar feedback, chemical enrichment, and of course, gas accretion onto black holes and AGN feedback. As for gas accretion onto the black hole, we assume that gas is accreted via a modified Bondi formula, and we also take into account the angular momentum of the gas which is accreted. As for AGN feedback, we model the distribution of AGN feedback energy to the different components of the multiphase interstellar medium according to the physical properties of the hot and the cold phases. Here we can see the evolution of the central black hole within the quasar-host galaxy at the center of the most massive halo of our simulation, and these projected density and temperature maps introduce our cosmological simulation, the innermost regions of our fiducial cosmological simulation. As you can see from these maps, the central quasar-host galaxy is embedded within a complex network of filaments. These filaments are made up of cold and dense gas, which funnel the gas from the large-scale structures towards the innermost regions of the forming galaxy where the star formation happens. And of course, a natural outcome of the star formation is the enrichment of the ISM and CGM in heavy metals, and we can see that gas metallicity can easily exceed solar values. we can appreciate quantitatively density and temperature for different phases of the ISM as a function of the distance from the galaxy center, and here I also list relevant masses. We investigated the star formation history of the reference simulation in red, and of a companion simulation. This is a reference simulation where only star formation and stellar feedback are included, so there is no quasar feedback in the light blue model. We can see that simulated galaxies are characterized by star formation rates which are as high as 200 solar masses per year at redshift 6, that's in agreement with observations. And we also find that quasar feedback can produce both episodes of positive and negative feedback. Indeed, quasar feedback can overpressurize the ISM and thus locally enhance the star formation, but of course it can also heat up the ISM and suppress locally the star formation rate. However, we find that the star formation history of these galaxies is not sensitive to the effect of quasar feedback, since it is almost completely shaped by the cosmological inflow of gas, which is accreted from the large-scale structure at redshift 6. So we expect that a longer-term and more cumulative effect of the quasar feedback is needed to suppress significantly or even quench the star formation later on. Besides the distribution of gas and stars, we can, of course, analyze the distribution of black holes within the simulated volume, and they are here color-coded according to their black hole accretion rate, and the black hole accretion rate of the central most massive black hole is of about 35 masses per year. We can investigate the location of black holes in the simulated volume in the black hole mass-stellar mass relation. So we calibrated the AGN feedback efficiency of our model so that the mass of the most massive black hole in the simulation is in agreement with high redshift observations. By doing that, we see that the distribution of black holes in the simulation is characterized by a slope which is significantly steeper than the slope of black holes in the local universe. This is something particularly relevant, since it is often assumed that the Magorian relation only evolves in normalization across redshift, while on the other hand, our study suggests that there is also an evolution as for its slope. Of course, we can investigate what happens if we adopt a higher AGN feedback efficiency, so that the mass of the most massive black holes is in agreement with observations in the local universe. In this case, the distribution of black holes in the simulation is characterized by a slope which is closer to that of observations in the local universe and way shallower than the slope of the distribution of the fiducial simulation. We also analyzed the evolution of the black hole mass growth for the two simulations that I've just introduced, and of a reference simulation where the black hole is present and can accrete gas, but no quasar feedback is included. We find that it is possible to produce a supermassive black hole as massive as 10 to the 9 solar masses by redshift 6, starting from initial seeds which are as massive as 10 to the 5 solar masses. We found that the accretion of cold gas always dominates over the hot phase, and of course we also find that gas accretion is the most significant process, meaning that black hole mergers contributes little to nothing to the mass growth of the supermassive black hole. We can also analyze the evolution of the black hole accretion rate, both in terms of solar masses per year and in Eddington accretion rate, and we find that a low agent feedback efficiency is needed so that the central black hole can be in agreement with observations of supermassive black holes in the high redshift universe. We also analyzed the distribution of outflowing gas in our simulations. Outflowing gas is promoted by the joint activity of stellar and AGN feedback, and we quantified the relevant importance of these two processes. We found that quasar feedback is able to accelerate outflowing gas to highest velocities and leaves a significant imprint on the high velocity tail of the distribution of the outflowing gas. Velocity of the gas in outflows are in agreement with observations, and of course we can also investigate the radial velocity of different phases involved in outflows. We analyzed the evolution, so we analyzed the radial velocity as a function of the distance from the galaxy center, and here we focus on cold gas and the hot and diffuse phase. We see that cold gas can be accelerated up to roughly 300 kilometers per second, while the more diffuse phase can be accelerated to larger velocities. I leave here with my conclusions and take questions.
Thank you very much. Questions from Milena?
Hi. Did you test your model on different seeding mechanism of the supermassive black holes?
No. We assume massive seeds, which are the likely outcome of direct black hole collapse scenarios.
Okay. So, and the mass threshold is?
So their seed mass is 10 to the 5 solar masses, and they are seeded in halos which are as massive as 10 to the 9 solar masses.
Okay, thank you.
Sorry, can you go back to the last slide? Not this one, in fact. Okay, the one with the different phases. So you are saying that the cold gas can be accelerated as at most of the order of a few hundreds of kilometers per second, but then the evidence that we have in the early universe from observations point out to even larger velocities for molecular outflows, at least looking at the references that were put before.
So when we say cold gas, actually we refer to both the cold and warm phase.
Okay, so it's not...
That the molecular gas makes up the bulk of the outflowing gas, but of course here we also include the warmer phase, which has a temperature of up to a few hundreds Kelvin.
Very last question.
No, I was just thinking that the hot phase, when by hot I mean 10 to the 6 Kelvin, I don't know if this is the temperature you have in mind. Okay. These velocities actually should have been seen already, at least in our galaxy, in oxygen 7 absorption, and we actually don't see such high velocities. I mean...
In our galaxy...
yes, they should have been resolved by the in absorption by the RGS, for example. The centroid is known to a few hundred kilometers per second.
I don't know whether it was a comment, meaning that we are focusing the analysis at redshift 6, and I don't see the connection with...
I'm sorry?
we are focusing the analysis at redshift 6, and I don't see the connection with observations.
No, I know, but if these objects have this velocity at redshift 6, probably also at lower redshift, the CGM should have this imprint, no?
It might be, maybe we can discuss.
Okay, you can discuss at the coffee break. We have to move on. Thanks again, Milena. And the next talk by Andrea Travascio. Let me read the title. Let me put it on. Okay.
Let me start. In the meantime, okay. Hi everybody, I'm Andrea Travascio, a postdoc in Bicocca Università di Milano. And today I wanted to present you some first results of a work in progress. Therefore, please, constructive comments are welcome. Work in progress in which me and co-authors investigate multiphase outflows in a hyperluminous quasar with unprecedented spatial resolution with narrow field mode muse data. So, studying multiphase outflows is interesting because it helps to get more information about the agent feedback, therefore how the agent can impact the host galaxy evolution. And here, just briefly, let me say that, as also Maria Vittoria mentioned before, the energy released by the AGN as jets or relativistic nuclear winds, but also radiation, can have an impact on the multiphase interstellar medium, triggering galactic scale multiphase outflows. And the situation is a bit more complex. Indeed, there are a lot of questions regarding, for example, the way in which the energy is transferred to the multiphase interstellar medium, but also about the expansion of these galactic scale outflows. We don't know if multiphase galactic scale outflows are triggered by the same mechanism. We don't know what is the geometry of these multiphase outflows, and we don't know what is their impact on if they have a different impact on the galaxy evolution. Therefore, why PDS 456? Well, PDS 456 is studying PDS 456 is a great opportunity to investigate multiphase outflows in a very important detail, in particular if it is studied with narrow field mode muse data. For two reasons, actually, because here you can see a plot redshift versus barometric luminosity by use metal, in which they show also different characteristic of AGN in sample studies so far. And you can see that PDS 456 represents the most luminous quasar in the local universe, and it can be seen as a local counterpart of hyperluminous quasars shining the cosmic noon, like for example Wish quasars. What this means? It means that we have a laboratory of hyperluminous quasar where we expect to have a high efficiency of AGN feedback, radiative AGN feedback, in the local universe. Therefore, thanks also with a powerful integral fast spectrograph narrow field mode muse data with adaptive optics, we can achieve a value of the PSF 0.08 arc seconds, and therefore it could be 2-3 times lower than typical PSF that we would have by looking at Wish quasars, for example. Second reason is that it hosts very important, very powerful winds, the most powerful ultrafast outflow never observed, but also warm absorption and broad absorption line of outflow in carbon-4, each of them with velocity 0.3 speed light, and also by Bischetti et al. With ALMA has been detected an extended blue-shifted and uncentral red-shifted molecular outflow. So, going to see the results, the first results. By subtracting PSF and continuum of the quasar, we can study in this data the H-alpha emission line, nitrogen 2 line, and sulfur 2. Here I show you a surface brightness map of the spatially resolved H-alpha emission, and the Greek contours here represent the morphology of blue-shifted molecular extended outflow. detected with ALMA. You can see just here a correlation, a spatial correlation between the multiphase gas, therefore ionized atomic gas and molecular gas, and also a Clampich alpha region at the position of the bulk of the molecular outflow, suggesting probably a connection between them. And looking at the kinematics, kinematics maps of the H-alpha, spatially resolved H-alpha emission, you can see, here, you can see here this velocity shift map, and here the velocity dispersion map. The dashed black contours again are blue shifted extended molecular outflow, while here you see the central red shifted molecular outflow in a black solid line. While here you see the same velocity kinematics map for the molecular disk detected with ALMA. And you can see that here we have extremely larger velocities than what we observe in the molecular disk. And also the morphology, the kinematical pattern suggests that this H-alpha emission is probably tracing outflow. Therefore, what we assume here, and is plausible, is that this represents ionized outflow observed in the narrow line region. And you can see that we have, it is spatial correlated also the high dispersion region with the molecular outflow. Looking at the kinematics in these two regions, in particular the blue shifted components, both in molecular and ionized outflow, and the red shifted central components here, you can notice a strong correlation between the kinematics of the CO32 emission, the molecular outflow, and the ionized outflow. You can see here black spectra extracted from ALMA in the same region of colored spectra extracted from MUSE. And you can see that for the blue shifted component we have same kinematics of H-alpha and CO32 emission shifted at the systemic redshift of the quasar estimated with CO32. And here we have to compare the wing of these emission lines, that it is due to the fact that in ALMA we have not subtracted the PSF, so we are observing the molecular disk. And this line is the H-alpha line, and also here in this case they have quite similar kinematics. So what we found from here is that we have a spatial correlation, we have similar kinematics, except for the fact that for the ionized outflow we have a shifted component that we don't see in the molecular phase. Now, deriving from the question what properties these gases are, we are going to see the nitrogen 2 H-alpha emission map. And what you can see here is that there's a interesting drop in nitrogen 2 H-alpha emission that is spatially correlated both with H-alpha clumper region, but also with the bulk of the multiphase outflow. Now, what we can do is just looking at extract the nitrogen 2 H-alpha emission in these regions, and as we have also wide-field mods MUSE data for this object, but I don't have time to discuss about that, but we have in that data information about oxygen 3H beta. We can also extract from here this information about oxygen 3H beta ratio line in these regions because they have the similar size of the PSF of wide-field mod MUSE data. And by extracting this and putting in this BPD diagram, we obtain these 3 points here. The red one is the drop nitrogen to H-alpha line ratio. And we compare it with a cloudy photoionization model from G et al., in which they assume a typical AGNZ. And you can see that, surprisingly, the points follow the trend of these grids. In particular, suggesting that this gas, emitting gas in these different regions, can be considered at the same metallicity. Indeed, you can see here fixed metallicity for these lines and fixed ionization parameter for these lines. And similar electron density that we could fix at 10 to 4 centimeters minus 3. And what exchange is the ionization parameter. And this is not strange because there are a lot of other observations showing that a drop in the nitrogen 2 alpha emission corresponding to the presence of a ionization cone. Therefore, what you're observing is that the bulk of these multiphase outflows corresponds to a region in which there's a ionization cone here. Very well. So, okay. So, taking all the kinematics map morphologies and what we obtained from the first results, we can develop a scenario for the geometry and the expansion and the mechanism involved, the geometry and then, well, the spatial correlation between multiphase and ionized outflow. What we can see here is that, okay, based on the Martedì kinematics, we assume that this has a holoconchal geometry, the ionized outflow that I show here, while the molecular disk is observed in face-on according with the estimations in Bischetti et al. With a slight angle of 25 degrees with respect to the line of sight, while looking at a different perspective in which here there's the line of sight and here the XY plane in which the maps lie, you can see that the angle of the ionization cone has to be, is not perpendicular to the line of sight, but we have to consider an angle in order to explain the fact that we are observing a blue shifted component at larger distance from the center with respect to the red shifted component. Moreover, the presence of only a blue shifted molecular outflow suggests that the molecular outflow has to be in front of the ionization cone, and therefore we are assuming that this configuration, and in particular we assume also that the molecular disk has to be oriented in this way in order to explain molecular outflows as sweep molecular gas after the impact of radiation or winds. The nuclear region is difficult to constrain, while the redshifted central multiphase outflows can be explained in the same way, therefore is a mirror case of this site. This is how it's possible thanks to the high resolution that we achieved in this data. While if we want to be sure about the same, I mean, we are suggesting that probably the molecular ionized outflow are triggered by the same mechanism. To be sure about that, we need to see the energetic properties of these outflows. Here I show you bolometric luminosity versus mass outflow rate and wind kinetic power. And you can see that these are values obtained by Fiore et al. Assuming a fixed electron density 200 centimeters per 3. These in blue and yellow crosses are molecular and ultra-fast outflow in PDS456, while stars represent ionized molecular outflows considering different electron density that are very hard to constrain in this case. Let me just focus on the chain one, therefore the 200 centimeters minus 3 that is that one that allows us to compare this PDS, this ionized outflow with the rest of the population observed in gray color here. And the 10 to 4 centimeters minus 3, that because it is the most plausible electron density considering the photonization cloudy models. And you can see that we have not conclusive hints about that, because just say that if we assume a low electron density, we can say, okay, this is a very powerful ionized outflow. It has very large impact on the host galaxy, and go on, okay, it's what we expect, because this is a very high luminous quasar. If we are considering the high electron density, we say, okay, we have similar energetic properties of the molecular outflow, and therefore it's the fact that the molecular ionized outflow are triggered by the same mechanism is more strength. Also, this plot is very complicated, but anyway, let me skip about it. And so these are conclusions. Thanks.
Thanks, Andrea. We have just one question for Andrea. We are running late. There are two at the same. Okay. If they are very quick, we can have two.
Yes, no, just if you can go back to the previous slide about the conclusion on momentum or energy conserving, yes.
Sorry?
No, if you just comment on this slide.
Yeah. Well, the fact is that here we Biscotti et al. Found a very low value that was expected against the theoretical expectations, because it suggests that we are observing a molecular outflow in a momentum conserving regime. And what we expect is that, okay, we assume that due to the high volumetric luminosity, we assume that the ionized outflow dominates the system, and so we expect to have something like that. And therefore, in this case, we could suggest that we have an energy-conserving scenario. Looking at high electron density, we see that it's not. It's similar to the. We are not able to achieve the energy-conserving regime. So, I mean, It's not conclusive here, but the fundamental things should be constrained on electron density for this system, and this will be the next step.
Okay, thanks again, Andrea. And we move to the last talk of this morning. We have Bartolomeo Trefoloni talking about understanding the nature of X-ray weakness, the case of the most luminous blue quasars at redshift 3. And let me... Okay.
Can you hear me? Yes? No? Yes? Okay, thank you. Thank you, and thanks to the committee for giving me the opportunity to share my work with you. So my work has been devoted mostly to understanding the nature and characterizing the properties of a sample of very luminous quasars at high redshift. Okay, just to give you some brief information about this sample was built in order to investigate properties and the interplay between the X-ray coronal emission and emission from the disk at very high redshift. So in order to have a clean view on this topic, we selected those objects in order to fulfill some basic requirements. So, for example, no, the pointer doesn't work. Okay. So, for example, we wanted to exclude objects with broad absorption lines, or objects which are radio loud, or even we wanted them to be very luminous, so something like almost 10 to the 47 erg per second. And we also wanted them to be, okay, it works. We also wanted them to be with the leastly affected from emission, yes, extinction. So just to give you an idea of where this sample locates in comparison with other samples, we see that this is located here at redshift between 3 and 3.3, and it detaches from the main body of the SDSS 7th release of Quasars in the very high luminous tail of it. Okay. No. Okay. No. It's very sensible. Okay. Yes, we embarked on a multi-wavelength mission in order to sample each possible relevant band of the spectra of these objects. So we have, for example, XMM Newton dedicated observation for the X-ray part. We had some archival data from the SDSS for the Lyman alpha region. And we also had the possibility to use the LBT observatory to get some spectroscopic data of the MG2 region and on the optical side. So just some quick results from previous works. The beginning of it was in 2019 with the analysis of XMM data, where the first surprise happened. So despite the very homogeneous degree of properties in the UV side of the spectra, we found two distinct samples. So the main body of these 30 objects displayed very typical X-ray properties. So for example, I have a photon index which is 1.9, which is great and in line with what we observe from lower black hole mass quasars and lower redshift and bolometric luminosities. And also we see that the fluxes, the X-ray fluxes, are the ones which we would expect for such luminous objects. This is an example of one of those. And we call them the X-ray normal sample. On the other hand, we see that almost 25% of the other objects display flatter photon indices and lower fluxes, and we refer to them as the X-ray weak sample. Overall, we also see that, as I said, the photon index is in line with what is expected at lower redshift, and this is great because this is telling us that probably the emission mechanism for quasars is kind of ubiquitous through cosmic ages. So it makes look like them if they were kind of standard candles. And moreover, we also find that X-ray absorption is never statistically very significant in the samples. We then moved on the archival data of the Sloan survey, and we still found some differences because, for example, we find that weak quasars display a flatter continuum, and also a broader carbon-4 profile, whereas the normal ones behave very well in the sense that they have very homogeneous properties, and in fact they are part of a sample where the X-ray to UV luminosity relation it's very, very tight. And for other information, please refer to Matilde Signorini, Stolk, and Andrea Sacchi's poster, which are great for this topic. Okay, now what to do now? Okay, so the question I'm asking is, we see some differences between those objects, but are these differences real? So we find throughout all the spectra, or are we missing something? And in case this is real, as we believe, what's the driver behind these differences? So it is about the governing parameters, is it about the accretion state? So to this purpose, we embarked on, as I said before, LBT dedicated observations, and we got some spectra, 29 of 30 for the ZJ band, which correspond to the rest frame MG second emission, and only, unluckily, 9 out of 30 for the optical side of the emission, which includes the H beta region and the oxygen third. So the goal is obviously trying to connect the observed differences in the X-ray properties with some possible differences also in these sides of the spectra. To do this, what we did is just to perform a detailed spectroscopic analysis on each of the sources, the 29 plus 9 objects, in order to infer the broad line and also the narrow line region parameters, and also the governing parameters such as the black hole masses and the Eddington ratio in the most reliable possible way, which is not so easy. So skipping to the results, this is for what concerns the magnesium second region. We found that on average the continuum is still flatter for X-ray weak objects, which leaves room for a higher incidence of iron emission, and also a higher incidence of iron over Mg second line ratio, which is what we would expect from some others prototypical X-ray weak sources such as PHL 1811. And moreover, we also were able to derive 14 out of 29 black hole masses from MG2. Unluckily, other 15 were not. We were not able to get them because of some bad transmission region just falling on the MG2 line, which is unlucky. And this is important because so far we only had at our disposal carbon-4 masses, which are not so reliable. So if we look at them, if we look at the MG2 over iron, iron over MG2 emission, and we compare these with other literature samples, we see two things. The first is, as I was saying before, there is a difference between those two samples that here I have appointed as blue and red stars. And here I also put the PHL prototypical source, and I shifted it to a redshift for the sake of the comparison. And the other things that we find is that on average, the X-ray normal quasars are in line with the expectations for such redshift quasars, and we don't find any strong evidence for any evolution of this ratio through cosmic times, even though we must be aware of some systematics that could affect these kind of measurements. Moving on to the optical side, we found this time that on average the continua are much more similar than what we found on the UV side, and the optical iron over H beta emission is slightly larger for the weak sample, but maybe the most striking feature is the lack, almost the complete lack, of the oxygen third emission, which is kind of puzzling. Okay. Moreover, yes, we also derive some the masses from H beta, which are still more reliable than carbon-4. This, oops, it's very sensitive. Okay, perfect. This puzzling thing of the oxygen third emission gets even more intriguing when we match the sample with the low oxygen third with the ones that are also X-ray weak. In fact, we get a good overlap, if we watch here, between the sample with low oxygen third emission and the ones with low X-ray emission. Obviously, we are talking about just 9 objects, so larger statistics is a key requirement for stronger claims. But this also leads us to think that maybe these two deficiencies could be related. As I was saying before, we derived the black hole masses, and we want them to be as reliable as possible in order to also try to get the key parameters for these objects, which are the black hole masses and Eddington ratios. But we did not find any significant difference at all between the Eddington ratio and the black hole masses for these two groups of objects. And so they are not likely the main driver of these differences. In fact, they all have very high Eddington ratios. They all have very large black hole masses. So what could account for this difference? Maybe one possible explanation is the lack of UV photon seeds. We know that for the X-ray emission, we need UV photon seeds in order to be upscattered by an inverse Compton effect to produce the observed power law. But if a substantial amount of seed photons is depleted, for example, from outflowing phases, or they get trapped into the accretion disk when it is highly accreting, then this could explain the intrinsic lack of X-ray emission without needing to invoke, for example, absorption or some kind of shielding. And this could also explain and be important for the lack of the oxygen third emission. So I leave you here with the differences between the samples that we found in this work, and thank you for your attention.
Thanks. Questions for Bartolomeo?
Well, I'm a little bit surprised by your result, but I wanted to ask you whether you could measure the Fe2 intensity normalized to the H-beta flux in the optical, and which are the typical value for the two groups of sources?
Okay, thank you for this question. But before answering, I have to say that we were not able, and the answer is here. Sorry, I go back for a while. Okay, this. Okay, no, maybe it's better this one. Okay, usually, as you know very well, the ratio between the optical iron emission and the H beta is computed between 4,400 angstrom and 47 kind of. But in this case, we were not able to sample this region. So we tried to do it, but we had to rely on extrapolations of iron templates, which are not that reliable. So we tried, and we don't find a very strong difference between those samples. We also tried to plot them on the eigenvector 1 plot, so full width of H beta and iron ratio, but they do not display such a strong difference. What I said here is that we find anyway a difference in the iron emission, but it was computed only between 5,100 angstrom and 5,400 angstrom. And this was the best that we could do for this sample. But it will surely be important to do it also on the blue earth side. Kind of lower than 1, below 1.
Okay, if there are no other questions, thanks again to Bartolomeo and to all the speakers. To all the speakers of this morning session, and we reconvene here at 2:30.